I'm Bryce Villanueva.
I'm Eric Johnson.
I'm Paul Kelly.
My name is Jimmy Cabrera.
And I'm Connor O'Brien, and we are Team Gamers Rise Up.
The goal of this project was to build 3 Arduino systems that collected different types of data. Each system centered around 3 required types of sensor input, which included distance, water level, and temperature. The collected data would be shown with either a servo dial or a digital display. With many unique components, there were differences with how systems were calibrated and how data was collected. To create and test the systems remotely, our team agreed to have one member who was tasked with assembling and performing experiments, while the rest of the team assisted in data collection and analysis. Voice chats were very important to our strategy, as we could then understand and work out our problems. The first 2 types of systems we built were for recording distance and water level. This was done using the ultrasonic sensor and the water level sensor, respectively. This is a diagram that we use to wire our ultrasonic sensor. It works by sending out a sound signal, receiving that signal back, and then using the time elapsed between those 2 events to determine the distance. This is the wiring diagram that we used for the water level system. It works by using multiple and parallel conductive lines of metal that can change resistance as the water level changes. By measuring the resistance values, we can convert to determine distance at several levels. Before we go out and record our data, we need to figure out how to calibrate it and then display it. For calibration on both systems, the general idea was to plot the known measurement, done by a ruler, versus the recorded sensor data. We created a linear regression on this plot and implemented it as a function to our Arduino code to calibrate raw sensor data. We were required to read off of our data through a servo dial. So we created a mapping function that essentially just takes in our measurement and outputs a degree value so that we can tell the servo how much to turn. So for example, if you could say that every centimeter is 2 degrees, and we get a measurement of 4.5 centimeters, that would result in 9 degrees of rotation. So we would just tell the servo, move 9 degrees. So this final diagram is essentially how our code works. We take in some kind of input data from our sensors and throw that into a regressed linear function so that we get a better estimation of our data. Then we put that in a mapping function, which gives us a degree value so that we could tell the servo how much to turn. Then we would read off of that servo dial so that we could write down the measurements for further analysis. This is a demo of the distance system. As the box moves closer to the sensor, the indicator moves clockwise. And as the box moves away, the indicator moves counterclockwise. Each tick is made every 22.5 degrees. So this is red, so we can determine the distance value. This is our water level system in action. As the sensor goes down, water level increases. Therefore, the indicator moves counterclockwise. As the sensor goes up, water level decreases. Therefore, the indicator moves clockwise. Now, measurements can be done just like in the previous distance system. Each system has its own quirks. The distance system has a low resolution of just a centimeter, and the water level output is so inconsistent that it's terrible to use. Finally, reading values from a dial is imprecise and difficult. The final system that we built was the temperature system. This was built using a thermistor, and instead of displaying our data with a servo dial, we used a digital display. The temperature system was built according to the provided Arduino instructions with no modifications to the code or the system itself. The temperature system is made up of 2 components, the thermistor and the LCD. The thermistor is really just a resistor that can change its resistance depending on the temperature. That means that when we try to read the value of it, we can convert it into a temperature and record that for our measurements. The LCD is a digital display that will be used to show our measured values from the thermistor. It also has a potentiometer to change the brightness level. There were 2 main issues that we encountered in creating the system. Firstly, we received 3 wrong components, but we were able to get the other 2 recovered from RTA. The other component was a resistor, and while we did get one, it was a wrong value. And that leads us to our second issue. What ends up happening is that our data is very, very precise, yet super inaccurate. And we'll demonstrate this in the next video. Here's the temperature system in action. As the thermistor is put in the hot water, the display changes to reflect the temperature. What ends up happening, however, in all of our measurements is that while the temperature is actually quite precise, the temperature is consistently off by 54 degrees Celsius. In the end, we resolved this and many of the other issues in other systems of this project by creating a regression function, which adjusted for these anomalies. The distance system revealed to us that low resolution can limit our measurements, and this is important when we as engineers might need to measure the difference of a few millimeters in a small part. The water level system showed that some tools can be highly inconsistent, but may be better suited for other tasks. In this case, the water sensor could be better applied for detecting if a plant needs water, instead of measuring volume in a container. Finally, the temperature system showed that high precision isn't everything, and why it's important to calibrate our tools, which is needed when using a strain gauge and many other digital instruments.